Okay, so yesterday we got to know the arc length, and then we introduced another one, which is the surface area. The surface area, if you remember, it also includes the arc length. Precisely this part here. Okay, this is the arc length, right? So when we apply this arc length, it's basically this one, this L. That's why that L will have the conditions for your integration. Is it dx? Is it dy? Okay, and then it will help you to navigate. What should you integrate? Which variable you want to integrate? So, as a conclusion from this part, then we have this. Okay. So either the conditions is the shape is like this, which the radius is this one, right? 1. And then the other one, the radius is x. You can keep y and x as it is, as long as it is the same variable that you integrate. Okay, that you integrate. For example, if, for example, your ds will be dx, the integration, which means that this y need to be equal to x. You need to find a function that is going to equal with this y, okay? Which means that this y here. Okay? So you can imagine this is actually like a function here, and then you rotate, similar to what we have in the volume before, right? So we need to define the functions. Okay? This is the function. But of course, we can define x equal function of y or y equal function of x. It's up to you. So basically, it depends on this dx. Which one to use is basically you can use both. You can use dy, you can use dx. But the important thing, before you decide to use dx or dy, you need to set up this first. Okay? You need to decide. Okay? Oh, if you have this kind of shape, then okay, this will be the radius. But you can write this first before writing the final formula. And then for this one, the radius is x. Then just write first, and then decide to choose whether we integrate with dx or dy. Okay. Okay. Let's see some example. This is actually an example from the textbook. After some example, we go for exercise. Okay. I will take some problem from the textbook. Okay. Now let's see. We have this. Okay. Example 1. So you have the function itself. That one is already in the y equal function of x. Okay. You have the boundary, -1 to 1. Okay. Which means that that will be the area that needs to be, or this, the area that needs to be integrated. Okay. And then what else? Okay, of course, this is. I think a conclusion that is from this function, this is actually the same thing, right? Circle equation. And then find the area of surface by obtained by rotating this arc about the x-axis. It has the picture already, so we can focus that this is the functions, and then we rotate through x-axis, something like that. Okay. So it's like maybe a bowl, right? Although it's like a bowl, maybe for dogs, maybe. Yeah.
If we get under this test name or graph, should we write the graph and how the figure seems?
The graph is actually to help you. Okay?
But is it necessary for you?
Depends. Sometimes some question doesn't really need to write the graph. Okay. I think that should be okay. If you feel that you can directly working on that, I think you can. I think for question like this, you can directly write, because you can imagine this graph is okay. This graph is like a square of x, right? Like a square root of x, and then it has the x squared. You can use transformation, and then you can imagine. But if you feel difficult to imagine, then maybe draw a little bit, it's okay, just to help. Now, this will be, okay, I think if we take this as a radius, right? So our radius is y. Let me write just y here. So this will be 2 pi y dx, right? Integrate like that. And since we have x already explicitly mentioned, so maybe we try to find according to dx. So we find the dx integrating with respect to x. Let's say this is going to be -1, or I mean, let me write later, okay. Just to make sure that when I put this -1, that would be the x. So this will be 2. Let me just write y first here, and then write the ds. The arc length is this. Okay. And now, what should we do next is we need this first, the first derivative. We already have this, then we need to derive, and then we have this y. We need to also substitute this y into the function of x. Okay. So let me start with the dy dx first. Let me write here. Dy dx is equal. Let me write here y is, just to help you to look for functions. So this is half, so we derive, so half 4 minus x squared, and then minus half, and then multiply with -2x. Okay. So this will be, so we can cancel 2. So we have x, -x over this -half coming down and becomes like this. Okay. Okay. Now we put this part, or if you want, you can take the squared. Maybe take the squared like that. And we can simplify it. It becomes x squared. And then this will be 4 minus x squared. Now let's put everything into this. Okay. So this will be, I will factorize the constant. And then y is square root of 4 minus x squared. And then still we have the big square root. This will be 1 plus x squared 4 minus x squared dx. Okay. Now we need to work on the algebra here, right? So let me write on maybe here 2 pi. Make bigger. So this will be 4 minus x squared. So this will be 4 minus x squared plus x squared. So the x squared will be cancelled. So this will be, or let me just write 4 minus x squared plus x squared, right? And then the x. Now this form, we can simplify it. I try to make it slowly so that you can follow. So we can have this, and square root of 4 we can have 2, right? So Okay, magically we can cancel. Okay. So this will be 4 pi integrated from -1 to 1 dx. Or this will be 4 pi. Dx become x if you integrate, right? X from -1 to 1. So 1 minus minus 1 is 2, so it will be 8 pi, right? So in the integration part, there is, I think, no complexity on the integral. We can integrate directly. However, sometimes we may need some techniques to integrate. So the most cases, taking substitutions or perhaps integration by part. But mostly substitution is enough. Okay, just to substitute. Okay, that's example 1. There is another example 2, but I skipped example 2. This is the same thing, similar. I will go for example 3. Okay, any questions first? Anyone should be understandable, right? Not too all right. Okay, let me zoom out a little bit to give you room for another questions, which is the example 3. Okay, I hope you can just see the picture first. Okay, if you maybe the word's too small. So basically, this is saying that we have a parabola y equal x squared, which is this red line, okay, from the x equal 1 to x equal 2, rotated through the y-axis. And then we need to find the surface. And the picture already gives you points, 1, 1, 2, 4, according to the x squared. So again, first we need to set up our x formula. Now the radius is x. So just write that first, okay? Before we compute and calculate everything. You just write the first formula. Okay. So just write first that this will be s. I just write simply 2 pi x ds. Okay, that's the first thing. You can write first. And then, since we have the y equal x squared, you can have two choices. You can have two options. Either you use the y equal x squared in terms of function of x, right? Or you want to change x equals square root of 1. It depends. The result should be the same. But I think x squared is much more convenient for calculation. So let's just keep this as a function of x, which means this x is still x. We don't need to change the x. What we need to pay attention is the dx. We need to make sure dx integration with respect to dx. Okay? So this will be 2 pi x, and then just write all the formula for the arc length, and we write dy over dx squared dx. Okay, and then what else? X is 1, 2, 2, right? So 1, 2, see this s. And then in another page, I will write the first derivative. So for yx squared, so this will be just 2x, right? So we have now s, factor out 2 pi. This is still x, and then 1 plus dy dx squared, it will be 1 plus 4x squared dx. And it's also a simple integration, okay, which requires substitution. What gives you a clue to substitute? Okay. Substitute is basically to see how this works out. Functions, if you remember calculus 1, usually you can define the functions like maybe 2 functions. Okay? The first one is just x, second one is the square root. It's 2 multiplication function. So, if you see this has square and this one is linear, if you imagine this part can be derived, and then later you substitute, it can cancel this one, right? What does that mean is, basically, you can cancel the x part. So if we take u as a 1 plus 4x squared, and then we derive, and this will be 8x dx, then we can substitute the x with 1 over 8x du, okay? So what's happened next is we can cancel the x, okay? And remember, when we try to substitute, since we have the endpoints in x, but now we substitute to u, then we need to also change this, okay? So change everything. So when x is 1, u is 1 plus 4, 5, right? And when x is 2, u is, so 4, 16 plus 1, so 17. So this can be written as, so 2 pi, this will be 5 to 17. And then let me just write x, and then this will be 1 over 8x, and then this will be square root of u. This is the u, just to see that this will be canceling, okay? And then we can take this pi over 4, and then this will be u with power of half du. And this will be 2 over 3, right? So pi over 4, 2 over 3, and then u, 3 over 2, and then 5 to 17. Okay, so cancel this. So we have pi over 6, and we have 17 squared of 17, right? And then minus 5 squared of 5. If you want to use calculator, it's okay. If you want to make it decimals, that's also fine. Okay. Now, if you want to, maybe using a function of y, we can use x equals square root of y, and then change this dy dx become dx dy. Let me just write a little bit here. So we can also try to use, let me put this on the left, okay? So if x is square root of y, and then dx dy is 1 over 2 square root of y, then we can have the s. Now it's y, so it's from 1 to 4. This will be 2 pi Now it's square root of y, and then square root of 1 plus 1 over 4 y dy, and then you can just complete everything. Of course, this is, I think it's way more, a little bit complicated. Compare with this one, right? It should be the same result. This is if you exchange all to one. Sometimes we can do these two things. Wait. It can be solved through another substitution, but you need to multiply this where y goes inside. So y plus 1 over 4. And simplify, substitute, and then you will have the same result. This is just to show you that we can have like two options. Sometimes one option is more obvious, that it will be easier, that you can just choose that. The other one may be a little bit more, take more time, but it will be the same result, the same answer. And by the way, if you have the textbook and if you see the exercise, sometimes the exercise comes up with the letter T. So you see the number, and then you see the letter T. The letter T means you need to use some additional tools, either calculators or go to the Wolfram Alpha, which means that sometimes the end result cannot be solved through your own computation. So you need to have a computer to approximate the answer. That's just if you have the textbook. Okay. But if not, then usually it could be done in the paper. It could be done. Okay, any questions? Any questions? I think we can go for some exercise, maybe one or two more questions about this. Okay? Just to let you know what kind of question that might appear. For the outline and surface area, the question mostly, if I put it in the exam, mostly direct forward question. Okay. So this is the answer. Okay, let's go through some examples. Okay, I put just a few examples here. This is, I think, quite straightforward. Okay, maybe from 9 to 16 first. We have maybe which number you feel that is okay. I think, how about 10? How about 12? Okay, because it has an exponent. We can review a little bit the exponent part. So this is 12. And then from the 17 to 20, maybe 20. What is the function of 1 over 4x squared minus? Yeah, okay, interesting. So again, let's say 20. Okay. So maybe giving you a couple of minutes just to try in your head first. I think the key is for this type of questions, you see the boundary, right? It's already in y and it's also x, right? First, you can try that boundary first. I mean, the integration should be either x or y, based on the boundary given in the information. You could see first, and then see the functions, which means that if you have this, and the boundary is x, so we could directly try to derive first, and see whether it's too complicated or not. If it's too complicated, you can choose like maybe we need to rearrange the functions. But sometimes the functions may be a little bit difficult to rearrange, that you can just use as it is. I think that is quite straightforward. Okay, try number 12 and 20. The rest, I hope you can try at home. Later this week, I will upload the notes for our class. I think every week I will upload. So hopefully today we can finish this part, and then we move to chapter 10. So chapter 8 finished. So it's actually quite short chapter. There is actually another subtopics that I think I just skipped that one. It's more about applications in physics, but I think I just skipped that one. And then we just need the arc length and the surface area for now. Okay. So we have the number 12. The function is square root of 1 plus e, right? Now we could imagine what kind of functions this is, and I would say that since it has the square root, okay, it will be on the positive side, right? And then it has the e, which means it's going up, right? So it's safe to say that we can say the radius will be y, okay? So we can first write that. And then since we are given the boundary in x, so let's say we are going to approach the dx, okay? So we can find the first derivative. If I write directly, can you follow up? I will write the derivative directly. This will be 1 over 2 . Can you follow up this? The first derivative? Okay. I hope everyone can follow this part. Or you need to read it. Or not. This is actually coming up from the square root of x. If you derive, it will be 1 over 2 square root of x. If you have x with power of half. So the half coming down, so 1 over 2. And then the x, the half taking minus, right? Minus 1. It will be minus half. So that's why it's coming down, right? And then the chain rule, the derivative of the inside for 1 plus dx, 1 is become 0, dx still dx or exponent, right? So we multiply with the chain rule, okay? Okay, now we take the squared, and then what will happen? This will be equal e to x over 4. This will be, the square root will be gone, right? It's 1 plus e x, okay? Okay, I think we can write in the formula. So s is equal, and we focus on boundary x is 0 to 1, and then 2 pi. Y is the square root 1 plus e with power of x, and then the s will be that one. So this will be square root, big square root like that, 1 plus the dy dx squared, which is that part. So e with power of 2x, 4, 1 plus e, and then this will be dx. Okay? Okay, now we need to simplify this first, right? Okay, I think I will just zoom in first and make it smaller, or maybe later I will make it smaller. Let me just write this first. No. Okay. So this will be 4, or maybe let me write with different color just to help. 4, so this will be e 2x plus 4 ex plus 4. Okay, this I would say the algebra part is quite challenging, so I hope you can try. Okay? You can try by yourself. 4 e, right? Correct, right? So 4. Okay, at least this is the algebra. Okay. So what's next that we can try to solve? Any idea? I mentioned last time every arc length or surface area, precisely the arc length part, because it has the square root. Sometimes you have some kind of pattern or tricks that involves a. Anyone remember? Yeah. Factor not necessarily fully correct. What is that? Okay. Yeah. Yeah. So we need to find how to make this a perfect square. Factor may be correct, but it must be the perfect square. So I think this can be in a quadratic perfect square, right? And mostly the tricks that comes up to solve the arc length mostly are doing that quadratic part. So you need to think a factor that can be implied or applied here. Okay? So if we see here, if you are maybe trying to exercise yourself, you could make the e to the x as maybe a. Okay. So this will be a squared plus 4a plus 4. I think it's much more clear, right? So you can take the a plus 2 squared, right? Which means that we can do the same thing with our equations. Now we could make this e to the x plus 2 squared, right? And then don't forget the rest is 4 plus e to the x. Okay, now we can finally write down the whole thing, and then we can remove the square root. So 0, 1, and then 2 pi, or maybe let me write 2 pi outside, just to, okay. So we have square root 1 plus EX, and then square root, big square root. This is the factors, and for oh, why I'm writing the square root? Wait. Okay, this should be this, right? And then the x. Okay. Now, one by one, finally, we'll just write this. And then this will be, the upper part will be just EX plus 2, right? The bottom part will be 4 becomes 2, and then the rest is take the square root, so it has another square root, which magically we can cancel this, right? And then we can also cancel this part. Okay, now we are left with pi 0, 1 EX plus 2 dx. Then we can integrate easily by taking the EX. It's just EX, right? So this will be EX plus 2x from 0 to 1, which we can just plug in E plus 2 minus 1 plus 0, so just 0 like that. So we have pi E plus 1. If you in the exam, like I mentioned, you can use calculator, but if the question requires you to solve process by process, you need to show this process. The calculation part is just for the final terms. This is for final terms. Okay, any questions? So from my solutions, I'm not necessarily drawing because I'm sure that the 1 plus EX, square root 1 plus EX is on the positive, or in the quadrant that is positive. Right? So I'm pretty sure that we can make the radius on 1. Okay, if there's no questions, let me zoom out a little bit so that you can see number 20. Okay. Maybe zoom a little bit here. Okay. So 1 over 4, I think this is too small, right? Okay. Now we have another function. And again, I think this is safe to say that we have a quadratic and we have a logarithmic, but since they are in one combination, so you can see that this is again between this 1 and 2. You can, if you want to try test the number, you can also try 1, 0, or 1, maybe 1/2, or maybe 1 and 2. Try that one and then see how the functions will be. Is it on the top or is it crossing the axis? Okay. Just to make sure that we are doing this like in the correct way, and there is no anomaly in the graph. And I think it should be okay. If we put 1, this is still positive. This becomes 0. If we put 2, again, this is also a positive because we have this is. If we put 2, this will be 1 minus something here that is 2 is in decimals, right? Okay, so I think should be okay. Okay, now since the boundary is on x, so I think it is safe to say that we can try to derive with respect to x. So maybe try to find the derivative first. So this will be x over 2. And ln x derived becomes, anyone still remember? Yes, 1 over x. So this will be negative 1 over 2x. Okay? Now again, we have squared this part. Maybe expand a little bit. So this will be that. Minus, we multiply both sides. So 1 over 4, and then multiply by 2, it's half, right? It's half. And then plus 1 over 4x squared. So this is 4 dy dx squared. But I think again this is, if you see the pattern, it is obvious that if you plus 1, it will change the structure. So this is again another quadratic patterns that is going to be in our case. So you need to follow up the quadratic pattern. So let's just add plus 1 on the right and plus 1 on the left, on the left and on the right. So this will be x squared over 4. So 1 minus half is plus, right? Okay. And then if you follow up the structure, it is similar to what we have in the beginning, but we need just to make it plus, to make this, right? So we can make it another quadratic perfect squared. Okay? So make quadratic perfect squared. So this will be x over 2 plus 1 over 2x squared. This is already in form of 1 plus dy dx squared. And now, since we already have a perfect square, we are going to put this inside the square root, which it can easily cancel this, right? So that's why we need to make this is to remove the square root. So if you see this, the structure or the formula of the uplink, the difficult part is that it has the square root. So it must make sense or quite logic if you want to remove the square root first. Okay? So let's just put into the equations. Okay, let me just write first, and then we can have a break. Okay? So S okay, we could have a break first. We are going to continue. Okay, let's start again. And the graph here, if you want to, like if you're curious, you can draw through GeoGebra, or if you want to review your calculus 1, how to graph a curve from derivative, you can try that as well. how to do that, if you remember, we can try to find the first derivative. What is the meaning when we have this? This means that this is increased, right? I will review a little bit here. And when we have this will be decreased, right? The function decrease. And then what will happen if we have the second derivative? This will be going related to, or let me write here, related to concavity, right? So it can be, if we have positive, we have negative, this will be concavity upwards, concavity downwards, right? And that's just to, if you're curious like how to graph in calculus, okay? But now I will assure you that our curve is going to be, let me write this. Let me just erase. Our curve is, since it has the ln, it's going to be like that and then like that. And the maximum part is on the x equal 1. And 2 is maybe around here. So when we rotate this about y-axis, so we have this rotation, right? Or maybe let me just put this note. Okay. So we have the radius that is going to be x. Okay. So we have the formulations that is as, we are going to use the 2 pi x. So 2 pi x ds. Okay. And then let me write directly. This will be from 1 to 2. 2 pi, still x. And then ds will be the square root of, I will just put inside the one that we have before. We already calculated. So x over 2 plus 1 over 2x squared dx. Okay. So we're going to have as 2 pi. It will be cancelled. So we have I think I will go here. So 2 pi. It will be, can we try the, let me try this just to make sure. Okay. So this will be that, and this will be x. This will be cancel. So we have 1 over 2, which cancel with this 2 here. So let me just remove 2. Okay, so pi, and then x squared plus 1 dx. Which this is going to be 1 over 3 x cubed plus x, put 1 and 2, and this will be pi 8 over 3 plus 2, and then minus the 1 over 3 plus 1. Okay, I'm lazy to compute, so I will just end up there. If you want to compute, you can compute. Okay. It should be easy, but I'm lazy. Okay, so I hope you compute. Okay. Okay. Because we are going to move to a new topics. Mm-hmm. Which one?
A over 3, A over 3, A over 3, right?
Yes. 8. Okay. Yeah, 8. So the next chapter will be chapter 10. Okay? If you have the textbook, we move to chapter 10. Chapter 9 will be skipped. That will be on engineering of mathematics. Okay? Oh, bigger? The bigger one? Oh, let me give you the line. Okay. Okay, I will move to the next page. I hope you don't mind. I will have your TA prepare another questions for you next week. So, parametric equations. So, what is parametric equation? So, if you see this curve, and if you maybe not pay attention to the what is this, and see just the curve itself. If we use our definition on a function, and of course, if we take the vertical line, it crosses all the points, right? Like more than one, right? So in terms of just the line itself, it's not a function of x. But if you remember, if you learn in physics, I'm not sure you learn something. Kinematics, you learn? Like you have the position, velocity, right? Okay. 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 So anyway, in sometimes in physics, you can define x, y as a coordinates that is related to position. And maybe sometimes if it's related to kinematics, the teacher usually gives you another variable, usually time. From time. Maybe when time is 0, which one is your position, maybe here, and then you move out when you increase the t. So this is something similar to that. So that's why in parametric curve, the interesting thing is you get this type of curve can be done. Okay. Well, of course, you need to get the context here, which is there is an additional variable. So you can say that this fg or the xy is a position depends on the t. Okay. You could think t like a time. For example, maybe from this time, and in terms of the parametric here, the t can be start from t. Maybe t equal negative. It is okay. It means that it's from the past, right? And then it moves, and see that it has an arrow, right? It has direction. Okay. That is a property in parametric. So it's going through here, go there and there. Okay, that's parametric. So when we deal with this parametric, for example, I will start right here. That is t is a parameter that can be defined by x is f of t and y is another function, let's say g. And both of this we call what we call as a parametric equations. And the curve, of course, it will be called a parametric curve. And remember, it has a direction. Okay, it has a direction. So, if we, for example, would like to draw something like this, we have two positions, let's say x and y, and it has a function of t that is defined. Okay. If we try to pick points, some numbers for t, let's say it starts from -2, to 4, we could make something like this. -2. You could try by yourself, like when you plug in -2, try an x, try an y, you have this position, and it will change along when we vary the t. So when we change the t, the position changes, and you'll see this parabola. Okay? You see this parabola, and it has direction. Okay? And the directions depends on which t we try to input. Okay? So this is t -2, and then go there, go there, go there. So the graphs in parametric curves, it doesn't really feel the same as a function of single variable that we did before in calculus 1. So maybe you could see something like a graph like, maybe you will have like a loop like that. It could be done also, or like a heart like that. It could be done also. Now, just to make it simplified and make sense for your logic, this t should be the same parameter, right? X and y, it has t, right? So we can try to substitute and see whether we can solve the equation itself. Okay? Just to make sure that we are doing the right thing. So let's say we start from here, that t will be y minus 1. So if we put there, and if we try to solve this, what will happen is we have a parabola in terms of y squared, which is this one. Okay, just to make sure that what we did is okay, right? So if you check like point by point, you can also draw. Also, if you want to know what kind of graph, you can try to substitute at the t and then see what kind of graph in terms of x, y. Okay? So in general, if we set up, so in general, if parametric equation defined by x equal f of t and y is g of t, and then we can set some number for t, let's say a to b, then we call the FA GA the coordinates. This will be the initial point. Let me write, this would be then. Okay, let me move this a little bit to the left. And the F B GB, this is coordinate for the terminal point. Okay, so A is the start for the T, B is the end point. So now we move from the variable x or y, we move the new variable which we call t. So mostly we are using t, or sometimes we are using theta in terms of parameter. But most of the cases, the variable usually, the books usually use t. Okay? And from there, we're going to go into the calculus part. Okay? So what is the differences between the one that we have before in calculus 1 and when we include the parameter t. So maybe before we go to the calculus part, so let's see this part here. Let me put this. So let's say we have another example. We have cosine t and sine t for each x and y. And of course, it has given you the picture here, but let's say we have this two. Okay? We could start to go into our definition for this period from 0 to 2 pi, which is this is related to the angle, right? Angular. So we could start taking 0. First is taking 0 for x, for t here. Cosine 0 is 1. So we start from x equal 1 and y is 0. Start from here, 1 and 0. You could try an angle in between, which you can pinpoint everything here, and then maybe focus on this 4, okay? Pi over 2, pi, and 3 over 2 pi. When you have pi over 2, cosine becomes 0, and sine becomes 1, right? So it's perfectly 0, 1. And you can see everything connected. But how do we make sure, that this is, okay, this is a circle? Okay? Unless you want to compute everything using calculators and you make sure that, oh, I have all the points. It's also okay. But to make sure that, we could follow that. For example, if we observe that if we have x and then we take the squared and then plus y, if we take the squared again, this will be equal to, let's say this is cosine t, it has a squared, and then plus this is sine t, it has another squared. This is related to what we have here, cosine squared plus sine squared is equal 1. So this will be 1. So will be what this is about. In the Cartesian, this is a circle with radius 1, which is perfectly fit with our picture here. So this is 1, right? So this is radius 1. Okay. In the other chapter, we are going to see how we are going to move from this Cartesian into what we call the polar. It's not only, the differences is not only what will be in the formula or how to apply the calculus. The difference is also how we observe the graphs. Okay? Cartesian means all the point defined by a rectangle. Okay, what does it mean? Okay. It means that every time you point xy, let's say this is xy, you have this, you could define this in a rectangular manner, right? It would be different if you, for example, if you convert this into polar, the rectangular will be gone. It will be circle. Something like this. This is just an overview for the next part, okay? So a polar will be, let's say we have this, and then let's say we have this as a, just to help you to imagine. Like you can pinpoint everything, like maybe here, here, and there, which means that from the rectangular here for Cartesian, you have like a rectangular boxes, like the books that you first learn to write. You have like a small boxes, like you write letter, or like something like that. And in the polar, you will change your perspective. Before it was like this, rectangular. Now it depends on angle, right? Okay. This will be on the 10.3, the polar curves or polar coordinates. Okay. So this will be a polar graphs. And if you see later, the polar has a unique shape that can be sketched. like a flower, that it can be done also. So I hope you could get the basic. Okay? But what we are going to take care is the calculus part. Okay. So I think I will give you some additional resources that you could try to look on. What is the polar and etc. for next week courses. Okay. But for now, let's focus on the calculus part. Okay. So first, let's take the parametric one first. Okay. So this is the Cartesian. Okay. Okay, I will change the page. So we start with what we call as a tangent. And it's, I think, quite straightforward. So I will try to get into what we have before is let parametric curve is defined by x equal f of t and y is g of t. Okay. And we can set up y is a differentiable function of x, which means we can say that y is function of x. Or maybe let me write f in terms of the capital F, just to separate with the other parametric. Okay. So let's say we have this condition. Okay. So the first thing is x ft, y gt, and we have conditions that is y is a function of single variable x. So y is having a connection with x. Okay. But y and x themselves, they are also function of t. Okay. Now, if you remember how we connect everything with the chain rule, so let's say if we are going to, so let me write, so with the chain rule, we can start to write that if we have, or let me write with different color. If we start write dy dt is okay. Okay, if we start from here, then we can define this based on what we have as a definition. Then we can have this chain rule. And then from this perspective, we could rearrange the formula and then write the tangent. Okay, this, remember, the first derivative of a function in the single variable, it is related to tangent or gradient. Okay? So we can rearrange this form into this. Okay? Of course, we need to make sure that this dx dt is not 0. Because of course, if it is 0, this will be undefined. Okay? So, what does this apply, or what does this imply, and what is the consequences? So whenever you have a parametric curve defined, for example, you have an x with a function of t, y function of t, okay, and then from these two, you want to know the tangent of the graphs. So without changing everything back to dy dx, you could directly use dy dt defined by dx dt, and you get the tangent. You get the tangent. You get the equation of the tangent. Okay? Equation of the tangent, or maybe the gradient itself, okay? At the point that is going to be checked. Okay? We're going to see how we apply the formula later. This one, let me check. Okay. Also from this, we could implies that perhaps we could have, maybe it will be like this, the curve, right? Or maybe let me just write a more, having a loop like that. Okay. Just as a reference. If we would like to know what is the tangent at a certain point, for example, if we take this tangent here, this is the tangent, okay? And if this, and of course, the point now is not xy, the point is t. So maybe this is t equals something something, okay? At t equals something something, we have a tangent like this, okay? Or if you see this part here, we have a horizontal tangent, right? And maybe here we have a vertical tangent. That is now we can put into our sketch. So we have vertical tangent, we have horizontal tangent in the parametric world. Now if we are going to, for example, if you want to know like in which part, in which t, for example, in which t that is the curve is having a vertical tangent. And maybe the horizontal tangent, and horizontal has a perhaps two here and here. Okay? And it's, of course, if you remember what we had before, the t is different. Okay? So maybe, oh, I forgot the directions. So let's say direction from here. Go there, and there. Okay. So we need to know what will be the t here, what will be the t here. But to find the vertical tangent or horizontal tangent, we need to remember in calculus 1, we say horizontal when the gradient is 0. And we say vertical, remember if you use the limit? Yes, yes. So we could take the same approach. The horizontal tangent is when dy dx is 0, right? Which means in our case, in parametric, this is when dy dt is 0 and dx dt is not 0. Okay? So that is for horizontal. We know that the horizontal is when it's 0, right? How can it be 0? So this will be 0. So of course the top should be 0. And this one cannot be 0, right? It should be another number. And to make it the whole thing 0. Okay? Got it? So dy dt is 0 and dx dt is not 0. Now how about the vertical tangent? The vertical tangent, it should be quote unquote infinity, right? Should be infinity. Okay. To be infinity, you need to have some number divided by 0. So you need to flip the definition. So vertical tangent is when let me just write dx dt is 0 and dy dt is not 0. So we could determine the slope of the tangent, and the slope of the tangent, especially which part is horizontal, which part is vertical tangent. Okay. There's an example here, but I would like to explain another thing first before we solve the example. Okay, let me zoom out. And let me go through. Okay, now this is the first derivative. Okay. Now in calculus 1, we learned the first derivative. We know to find the tangent, equation of tangent line, etc. Right? And of course, in the parametric, we will also doing that later, finding the equation of tangent line. But another thing is we are having the second derivative, right? The second derivative in calculus 1. Now, what will be the second derivative of this? If you see the connection here, let me write again in the other page. So if we have dy dx is dy dt dx dt, right? What will be okay? I will just go explain. Usually I give you example, but now I just go explain everything. This is the first derivative. To find the second derivative, some of you maybe think, oh, okay, we derive dy dt, we derive dx dt, and that is the second derivative. It seems okay, but that is wrong. Do you know why it's wrong? Not exactly. Anyone know?
G2 over G2.
It's mean this is the second derivative.
But
Yeah.
what has it been?
Okay. Let me give you.
What is the question?
Yeah. What is the second derivative from the parametric? So this is actually similar to
While
d dx of
I
dy dx. Okay.
and the root.
So what's important here is if we are back to our assumption, x is function of t, right? Parametric. Y also function of t. But y also function of x. So if you try to derive the top, derive the bottom, you are going to break the rule that you set up. So we need to make sure that we derive with the correct formulation. So this means that this will be, we take d dt dy dx, and then dx dt. So this will be the second derivative. Okay. Maybe to make it clear, let me just write the first derivative in terms of ddt, okay? Just to see what is the difference, okay? So this will be ddt of y. This is ddt of x. Okay? So we need to be careful on this dy dx, okay? Because y and x, they are kind of have a connections as a function. Okay? So we cannot take the top derived, the bottom derived. It seems like that, like from this one, it seems like, oh, we just derive with t for on the top, we derive with t on the bottom. It seems that is the pattern, but that is not correct. The correct one is we take ddt for each one of them. But for this one, we need to keep this as a dy dx because they are connected. Okay. So that's why we have this. So actually, to connect this to this is they're basically the same. Let me write this with the singular with that so that you can see they're like what is this one. Okay. So this will be ddt x. Okay. So the one that you try to find is this. Okay. So change y with dy dx. Okay. So if you want to, again, derive one more time, okay, what you need to care is this one, okay, because they are always connected, while the other one is, you can like use the second derivative directly here. So if you increase the order, like the third derivative, fourth derivative, you are just replace this with the previous terms. Okay? Replace, and then that is how you do it. Okay, what time is this? Okay, it's 3 p.m. So I think we can go for example. We can go for example, and after that, maybe we can finish. Okay, example is here. Let me put this a bit. I will just go pick the example one, and maybe next week I will choose some problem from textbook. Okay, example one, curve defined by parameter equations, blah blah blah. That's our equation. Show that C, the curve, has two tangents at the point 3, 0. So what we care is we have these 3 zeros, okay, and find their equations. So 3, 0 is xy, the coordinates, which means that we could find p. Okay, we could determine the p, right? B, find the points on the curve or the C where the tangent is horizontal or vertical. We already did this before. How to make sure it is vertical or horizontal, and then we can find the points. And determine whether the curve is concave. What's concave means it's related to second derivative. Okay, so that's why calculus 1, you need to be able to remember all. At least the fundamental one. And let's sketch the curve. So this is actually sketch the curve, but in parametric. So we can start from the number 1, which is the tangents. So directly we can write the tangents as dy dx equal dy dt over dx dt. Okay. So dy dt is, we have y equal t cubed. So t cubed is become 3t squared minus 3 over 2t. Oh, I forgot. We just need to start from the point. So let's say point 3, 0. It means that x is 3, so 3 is t squared, which means t is plus minus square root of 3. And y is 0, so 0 is t cubed. Just to make sure that we are correct. this is t minus squared, right? Equals 0. So t is 0 and t is, okay, if you're not careful, you will miss out the 0. Okay? So we have plus minus square root of 3, which is the same here, and t equals 0. So we have 3 t's. Okay, 3 t's. Okay. That is on 3, 0, and then find their equation. Okay. Now we put all the t into the tangent equations. So we start taking t equal positive square root of 3. So dy dx will be 9 minus 3 is 6 over 2 square root of 3. This will be 3. 3 divided by square root of 3, it's square root of 3, right? This is first one. And then when t is negative square root of 3, dy dx becomes the same. This will be 6, but now it's having a negative. So this will be negative square root of 3. Okay? And then for t equals 0, we don't really need that for the tangent because it will be undefined. So maybe perhaps the vertical or horizontal, we need the t equals 0. So first we have this. This is the tangent. So let me write here. This is the slope, right? We need to find the equation. So we need to put all this slope into our linear equations. So we put everything okay. So first is this is y equals square root of 3 x minus 3. And the second will be y I forgot. This is on the point. We know the point is 3, 0. So we just put 3, 0 inside the linear equation. So 0, 3, and the m is from the slope. So we have two equations. Okay. Okay. I will let you digest slowly. So basically the first thing I did is deriving the dy dx using the parametric conditions, and we have this equation. Okay, and then we need to find which t that is related to the point 3, 0. So we find first when x is 3 is equal to t squared, right? The equations. So we find that there will be possibility for plus minus square root of 3. And another equation is when y is 0. So when y is 0, we have the parametric, and we have t equals 0 or t plus minus square root of 3. So I think we just need this plus minus square root of 3, okay, because if we take 0, it will be undefined. So we can skip the t equals 0 first. Now we can find the slope. We just what we do is basically we just plug in everything here, okay, and then the positive and the negative. Okay. check that out, and then we have these two values. And then when we have the values, it means the value of the gradient, the slope. Slope is this. This is linear equation that you have known since long time ago, right? So we just put everything 3, 0. On the point 3, 0, this is 0, this is 3. So that's why we have this and this. Identical. Which means that when you have the identical linear equations with different, or we have the opposite direction of the gradient, it is perfectly crossed, right? Which means that it is our equation. Right? Because if you read the questions here, the point 3, 0 has two tangents, so it will be crossing like that, okay? Because it has identical equations, okay? Okay, I think I will end up until here, okay? Number B, you can try it by yourself. Horizontal and vertical, you can look back what we have before here. Just use this condition. Okay? Vertical is when the dt equals 0 and the dt is not equal to 0. So you can try to find from this. So for example, for vertical tangent, you need to make sure that dx dt is 0. So this is 0, which means that t is equal to 0. And of course, when t equals 0, if we put here, it will be undefined, right? Which means that that is perhaps the vertical tangent. Because when we put t, it will be really large, because it's divided by 0. If we use limit, it will be closer to this vertical line. Okay, I hope you get that point. Okay. We're going to continue this maybe later on, next week. If you want to look what is the sketch looks like, this looks like this. Okay. This is a 3, 0 here. It has crossing this, and this is the horizontal tangent, and this is the vertical tangent here, which is t equal to 0. Okay. So I think that's it for today's class. We are not yet having any attendance first. Next week I will start. Zoom out. Okay.
This is the direct folder.
Okay, I think I have a.
I tried it anymore.